Hello everyone. This is a joint work with Samuel Chang. My name is Atici. I am from Department of Mathematics. Samuel Chang is a senior at the Geffen Academy of Mathematics and Science. Today, we are going to talk about Introduction to Fractional H-Discrete Calculus. I like to start with basic definitions. And then I'm going to introduce you fractional h-discrete operators, Mittag-Leffler type functions. Then I'm going to introduce you linear fractional order h-difference equations. And then Samuel is going to do some illustrations with Mathematica 12. Why is h n sub a? So first of all, let me talk about this set here. This is the set that we will be working on. This is the domain of our equations, our operators. So as you see, this is a discrete domain, and it has infinitely many elements in it. But I like to tell you more about this domain. It is a time scale. Time scale means it's a closed, non-empty subset of real numbers. So this is one of the closed subset of real numbers. So it is a time scale. This set is a bridge between natural numbers n and real number interval a to infinity when h converges to 0. This is a good choice for modeling purpose, and I had a joint talk this morning with Dr. Nak Wing, and we use the same choice for modeling, same choice of domain for modeling. An approximation, so I wanna next tell you what the operator look like. But before we start, let's go back to Calculus 1 course, and this is the definition of Newton's definition of derivative here. And as you see, I am using backward definition for the limit. And then we do approximation. Approximation means take this limit out. When you do that, you approximate this side with this side, and then y prime of t is approximately y of t minus h over h. Now, here is the definition of the Nabla operator. So you see where Nabla operator is coming from. It is coming from the limit definition of the derivative in continuous time. And this Nabla operator here we have, it is defined on this discrete domain. And here I am talking about how we do perform higher order derivatives. Higher order derivatives are as same as how we do take derivatives for the functions in continuous time. I like to continue with rising factorials power. Rising factorial power is something that we use all the time for discrete calculus. The reason is we like to have polynomials, and we don't use the polynomials of continuous time. We use the polynomials of discrete time, and with the use of this definition, rising factorial power. So I am talking about t to the 2 rising, t to the 3 rising, t to the n rising. Think of, and it is, as you see, it is defined by this Euler's gamma function, and this gamma function. You know that it is not defined at 0, and it is it has pole at negative numbers, all negative integers. Now, what is the point of using this h rising factorial power or function in for polynomials in discrete time? Here is why. Because when you apply Nabla operator to t to the alpha rising, for example, then you see alpha comes down, you subtract 1 from the power. So we like to have this power rule. That's why we are using this h rising factorial powers.
Hi, so Dr. Atisi's asked me to sort of give a visual representation of these two concepts she just explained, the timescale domain and the rising factorial here. Of course, it always helps to have a visual representation, especially when defining a domain that one isn't familiar with, in order to kind of get used to the new domain that we're working on. So I've used a one-dimensional number line here because it always kind of helps to see the possible values on a domain. And here I've changed h from 10 to 0. So you'll see that as h is 10, you only have 1 point on the domain from 0 to 10, which is at 10 itself. And I've set a equal to 1, but as h approaches to 0, we get more and more points, and eventually as h equals 0, we do get a continuous domain, basically, a very, very close to a continuous domain. So if you'll watch this visual representation here, you see more and more possible values enter this domain as h approaches 0. And as we near the middle and the end of this animation, we get the fact that these points are so close together, eventually as h gets very, very close to 0, we get basically almost a continuous domain, which is what is expected as h becomes very close to 0. So we'll also see that same phenomenon in future animations as well, where as h approaches 0, the discrete functions become very close to the continuous functions. So the same, like I said, with this rising factorial animation that we'll see here, we represent a rising factorial. Here you have in purple the graph of t squared, let's say, and y equals t squared. And over here we have the graph of y equals t to the 2 rising. And we change the h value, which will change this graph of t to the 2 rising. And you'll see that as h approaches 0, we get closer and closer to the continuous approximation. So as we play this, you'll see here that as you play this t to the 2 rising function gets very, very close to this t squared in continuous time, as you'll see here. And eventually, as h equals 0, they do overlap completely.
I'd like to continue with nabla H fractional sum operator. So I am sure some of you haven't seen this before. Actually, this is a very fairly new topic for mathematicians. And I am talking about, if you want to compare what I am talking about here with the continuous version, I am talking about integral of order alpha. So this nabla to the minus alpha means I am talking about integral for this discrete calculus. And here alpha could be any positive real number. So I am talking about half order integral, 1/3, 1.3 order integral. So here is the definition of fractional sum operator. So instead of integral, we say sum in discrete calculus. What else do I need to tell you? As you see, kernel, this is the kernel of the operator, and kernel has this rising factorial power.
So as Dr. Atici said, the nabla sum operator in discrete time corresponds kind of to the integral operator in continuous time. So as a comparison, we have graphed these two together. So as you'll see down here in the blue dots, we've kind of graphed one per unit here. The blue dots represent the nabla sum operator performed on the function y equals t. And this purple continuous time graph right here represents the integral operator performed on y equals t. So obviously with respect to t, that is t squared over 2. So this is an exact, purple is an exact graph of t squared over 2. So this these blue dots down here are the discrete that is supposed to correspond with this purple. So as you'll see, we vary this alpha operator, this alpha parameter between 0 and 1. And as this alpha approaches 1, we get a closer and closer graph from the sum operator, we get a near match between the sum operator and the integral graph. So as we'll see here, as it gets closer to 1, this rises, and eventually, theoretically, as it reaches 1, it will overlap with the integral graph here.
I like to continue with nabla H fractional difference operator. So once you know how to handle fractional sum operator, which is corresponding to a fractional integral operator, then fractional difference operator is combination of fractional sum operator with nabla operator of integer order. So for example, if alpha is 1 over 2, then you take the upper bound of alpha, so 1 over 2 as an upper integer bound 1. So in this case, n is going to be 1. So that you have 1 minus 1 over 2. This gives you 1 over 2. So you are doing 1 over 2 order sum to function f, then you are doing nabla operator to f. That's how we do calculate the 1/2 power 1/2 order difference operator in this discrete time domain.
So again, the same as with the sum operator, the difference operator is also or corresponds with the derivative operator in continuous time, as Dr. Atici also said. So this difference operator, we also perform this on the function y equals t. So again, this purple graph represents the derivative of y equals t, which is, with respect to t, is y equals 1. As simple calculus will tell you. But this, these dots, these blue dots on the way upwards, this is the nabla difference operator performed on the function y equals t. And again, as the alpha parameter approaches 1, you'll see in a second, this these blue dots, this discrete difference operator, will approach the continuous derivative operator. So you'll see me play this animation here, and then you'll see that it nearly matches with that. So theoretically, again, as alpha equals 1, this difference operator will give the same results as the derivative operator in continuous time.
I like to continue with power rules. So for power rules, okay, first of all, I mentioned about the power rule for integer order nabla case. So do we have similar results for fractional order? Yes, we do have. This is for sum operator. So as you see, if we apply any order sum operator to this, beta to the rising factorial power, please watch what happens to the power. And this is fractional fractional difference operator. And when we apply alpha, a fractional difference operator to the rising factorial here, this is the rising beta to the rising factorial here, then look at what happens to the power. And if you compare what we are doing with what we had in calculus course for derivatives and integrals, they are really saying the similar things for us. And in this setting, we want to make sure that these fractions are defined. Because of the gamma function has some, there are some poles for the gamma function, so we have to make sure that these quotients are well defined when we talk about these two properties. I like to continue with the Mittag-Leffler function. This is very famous function, and we do see this function defined by Mittag-Leffler, Gosta Mittag-Leffler. I believe it is 1953 or something. So we have here, so not 1903, I'm sorry. So in 1903, Gosta Mittag-Leffler first time defined this function, but what does this function do? This function generalizes the exponential function that we all know. Okay, so if you take alpha and beta as 1 here, then you have the power series of the exponential function e to x. Okay. Now, this is what I am saying here. Later, Ravi Agarwal, 1953, he generalized the Mittag-Leffler function for two parameters, and he defined it with two parameters. That's what he did. I like to continue with Mittag-Leffler type function for our case where we are working on h-Discrete domain. And here is the Mittag-Leffler type function that we have here. And I want to point out that when h converges to 0, this upper limit of the series becomes infinite, right? And just consider this as 0, this t sub 0, this t sub 0 as 0. So you are going to start seeing the series at 1, and the upper bound is going to be infinite when h gets smaller, approach to 0. So, but the good thing about this series, Mittag-Leffler function has some, convergence issue. So, but for our Mittag-Leffler type function, we don't have such issue because as long as h doesn't stay close to 0, this is a finite sum, as you see.
As Dr. Atici was speaking about, we also have a discrete version of the continuous Mittag-Leffler type functions. So for that, we're going to also get similar results, that as our h, which is our parameter, gets closer to 0 with, of course, the discrete domain, we get closer and closer to the continuous results for our Mittag-Leffler. So I termed this the E function because our discrete Mittag-Leffler type function is denoted with an E with several parameters. So putting this E function, graphing this E function here with different h values, various h values, gets these colorful graphs on the right hand side. And the one I've labeled here as continuous fractional Mittag-Leffler is the actual continuous Mittag-Leffler function developed in, of course, 1903 by Mittag-Leffler. So as you see, the closest one you see here is h equals 0.01, and as h approaches 0, it is undefined, but it gets closer and closer to this continuous function. So theoretically, this h equals 0 should overlap with this continuous function right here. And this is on a discrete domain, keep in mind. I have just connected these graphs. You'll see each of these corners. There's a point right there and a point right there, because it's very hard to interpret when they're not connected. So these are discrete graphs.
I like to continue with some properties of Mittag-Leffler function. And here I am talking about alpha fractional sum operator to Mittag-Leffler function. And I want you to pay attention to this sub-indices here. When I apply, and look at what happens to the sub-indices. And I want to do this for fractional difference operator. So alpha fractional difference operator, look at how the sub-indices changes. And here, another property that you are seeing, when you want to compare this Mittag-Leffler function with this Mittag-Leffler function, it is like, can we get some relation between the lead term Mittag-Leffler function and the Mittag-Leffler function? And then this last property is about fractional difference equation, that Mittag-Leffler function is satisfied, or Mittag-Leffler function satisfied. Now, I like to continue with introducing here linear fractional order h-Discrete equation. So in order to do this, let me tell you where the delay term is coming. So you start with this very simple eigenvalue problem, y prime of t equals lambda y of t. And then you take this y prime of t and write as a limit right hand side stays the same. Then you do approximation, and approximation means take this limit out. Then you do that. This when the limit out is out, this quotient is delta operator, and the right hand side stays the same. But if you shift this equation t unit left, then you are gonna get this delete term. There is a delay term in the equation. You have a first order Nabla equation here. Linear fractional order H difference equation. So as you see where this is coming from, I explained to you briefly in my previous slide. So I am getting this first order Nabla difference equation, and I am fractionalizing the equation, and I have this alpha power for the equation, so that alpha, I am talking about alpha order fractional difference equation here. Alpha is between 1 and 2. And this equation has this general solution, C1 Mittag-Leffler type function plus C2 Mittag-Leffler type function.
So for our last graph of the day, we present what Dr. Atici just described as the problem on that the previous slide. And she mentioned that there was also a comparison between the continuous function and the discrete fractional form function that was defined by y of t. So on the left-hand side, you'll see this continuous function. I kind of think it looks like kind of like jumping ropes, but as you'll see, the greater the magnitude of our parameter, the more times it crosses the x-axis. So this blue one is a parameter of 1, and then you'll see that the next parameter is this yellowish, tannish one that goes down crosses 1 time and loops twice, and then it goes on, like this light green one is the third. But you'll see in the discrete fractional case, and here the amplitudes don't change. They stay from -1 to 1. But in the discrete fractional case, we see huge changes in amplitude as this graph goes and fluctuates. So the first order, this blue, you'll see an amplitude of 1 here, but you'll see much either less or greater amplitudes as this order goes upwards. So that's our last animation for today.
Here are some references that we can mention here. This paper was published last year to honor Professor Johnny Henderson for his 70th birthday. And another reference is a book by Christopher Goodrich and Ellen C. Peterson, Discrete Fractional Calculus. This is a book that may be considered as a basic book for beginners, and it's also a book for researchers who are expert in this area.
Yeah, before we conclude, we wanted to say thank you to everyone who attended our talk today, and ask for any questions now, or if you can't think of them now, feel free to contact us later at our emails listed below. So questions?